CBSE Mathematics Class 11th, Chapter 4, Exercise 4.1, Question number 1. Question number 16. You see here, question number 16 is 1 upon 1.4, 1 into 4 plus 1 upon 4 into 7 plus 1 upon 7 into 10 plus dash dash plus 1 upon 3n minus 2. In the second bracket, 3n plus 1 is equal to n upon 3n plus 1. Say the given statement is a proposition Pn, which is again the same things, that 1 upon 1 into 4 plus 1 into 4 into 7 plus 1 upon 7 into 10 plus dash dash 1 upon 3n minus 2 into 3n plus 1, and it will be equal to n upon 3n plus 1. Now here we examine when n is equal to 1. Substitute the value of n in the first term here. You will get P1 is equal to 1 upon 1 into 4, that will be equal to 1 upon 4. Now in the right hand side, RHS, you see n upon 3n plus 1. In place of n is put n is equal to 1, so 1 upon 3 into 1 plus 1. So it will be equal to 1 upon 4 again here. We see that left hand side is equal to right hand side, and it is equal to P. It means that, it implies that P1 is true. Now, once Pn is true, the Pk, assume it that the Pk is also true, that is Pk will be equal to 1 upon 1 into 4 plus 1 upon 4 into 7 plus 1 upon 7 into 10 plus dash dash plus 1 upon 3k minus 2 into 3k plus 1, and it will be equal to k upon 3k plus 1. Now again we have to examine for being true that Pk plus 1. We can write the same statement here now. That is Pk plus 1 is equal to 1 upon 1 into 4 plus 1 upon 1 4 into 7 plus 1 upon 7 into 10 plus dash dash plus here 3k minus 2 into 3k plus 1 plus the new term, that is new term being the k plus 1, so it will be equal to 1 upon 3k plus 1 minus 2, bracket close. In the second bracket, 3k plus 1 plus 1, and it should be equal to k plus 1 upon 3k plus 1 plus 1. So left hand side, you see the left hand side from this point to this point, it is equal to k upon 3k plus 1. Now write it down here. Left hand side, that is k upon 3k plus 1 plus the new terms, that is 3k plus 1 minus 2, 3 into k plus 1, bracket closed, plus 1. Now solve it here. You see k upon 3k plus 1 plus 1 upon 3k plus 1, 3k plus 4. Solve it, you will get 3k plus 4. It will be, you see, in the both terms we are getting 3k plus 1 as a common denominator. So we can take it out. That is 1 upon 3k plus 1 inside the bracket k plus 1 upon 3k plus 4. It is equal to 1 upon 3k plus 1 into 3k square. You see, just multiply it here. You will get 3k square plus 4k plus 1 whole divided by 3k plus 4. Now we factorize it. 3k square plus 3k plus k plus 1 whole upon 3k plus 1, and in the second bracket 3k plus 4. So 3k plus 1 and 3k plus 1 will be cancelled. We are left with k plus 1 upon 3k plus 4. And this k plus 1, as it is, we have written 3k plus 4. That can be written like this also. That is 3 in bracket k plus 1 plus 1. If you solve, you will get the 3k plus 4. So the 3k plus 4 has been written like this. Now you see, this is the same thing that which we have written already. So that it is equal to the right hand side. Hence, proposition pk plus 1 is also true whenever pk is true. Therefore, by principle of mathematical induction, Pn is true for all n belongs to natural number. Now come to the question number 17. 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus dash dash plus 1 upon 2n plus 1 into 2n plus 3, and it should be equal to n upon 3 in bracket 2n plus 3. We can write Pn such that 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus dash dash plus 1 upon 2n plus 1 into 2n plus 3, and it is equal to n upon 3 2n plus 3. So now we examine it. In place of n, we take P1, that is left side, the first term, that is 1 upon 3 into 5, that is equal to 1 upon 15. The right hand side will be your 1 upon 3 in bracket 2 into 1 plus 3. That will be equal to 1 upon 3 into 5. Again, it is equal to 1 upon 15. Assume that the pk is true for some natural number k, that is 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus dash dash plus 1 upon 2k plus 1, 2k plus 3, and it is equal to k upon 3 and inside the bracket 2k plus 3. Now here we need to prove that pk plus 1 is also true whenever pk is true. We have the pk plus 1, you see, just write down the same things. 1 upon 3 into 5 plus 1 upon 5 into 7 plus 1 upon 7 into 9 plus dash dash 1 upon 2k plus 1 into 2k plus 3, this much, and this is the new terms which has been included for being k plus 1, means the k plus 1th term. So it will be here written 1 upon 2k plus 1 plus 1, 2 into k plus 1 breaking in bracket closed plus 3, and it should be equal to k plus 1 whole upon 3 inside the bracket 2k plus 1 bracket closed again plus 3. The left hand side, you see this much, can be written like k upon 3 into 2k plus 3. here I have written it, k upon 3 2k plus 3 plus 1 upon 2k plus 1 plus 1 in the second bracket 2 into k plus 1 plus 3 bracket closed, that will be equal to k upon 3 2k plus 3 plus 1 upon 2k plus 3. You solve it, you will get 2k plus 3. Here you will get 2k plus 5. You solve it, you will get 2k plus 5. Now it will be equal to, I have taken 1 upon 2k plus 3 common, you see here and here. So I have taken 1 upon 2k plus 3 common in the denominator. The remaining part is k upon 3 plus 1 upon 2k plus 5. Now just solve it, you will get the 2k square plus 5k plus 3 whole upon 3 into 2k plus 5. Solving it, that in this 2k square plus 5k plus 3 can be factorized like this, that is 2k plus 3 into k plus 1 whole upon 2k plus 3 into 3 inside the bracket 2k plus 5. So 2k plus 3 and 2k plus 3 from the numerator and denominator can be cancelled. We are left with k plus 1 upon 3 inside the bracket. This can be written like this, that 2k plus 1 bracket closed plus 3. Thus pk plus 1 is true whenever pk is true. Hence, by the principle of mathematical induction, Pn is true for all natural number. Now come to the question number 18. You see 1 plus 2 plus 3 plus up to n is less than 1 upon 8 2n plus 1 raised to power 2. Let Pn be the given proposition. So the Pn is equal to 1 plus 2 plus 3 plus dash dash plus n is less than 1 upon n or 1 upon 8 inside the bracket 2n plus 1 whole square. Now examine for 1, when n is equal to 1, you see, take P1 is equal to 1, that is left hand side. Now put the value of n is equal to 1. On the right hand side we will get 1 upon 8, 2 into 1 plus 1 whole square. Solve it, we will get to 9 by 8. It means that it is 1 and 1 by 8. We note that the Pn is true for n is equal to 1 since 1 is less than 9 by 8. Assume that the pk is true. That is, pk is 1 plus 2 plus 3 plus up to k, and it is less than 1 upon 8 inside the bracket 2k plus 1 whole square. This is the second. We shall now prove that pk plus 1 is true whenever pk is true. We have, so we write it down here, that pk plus 1 will be equal to 1 plus 2 plus 3 plus 2 up to the k plus 1. Here the k plus 1 is the last term, so I have written it. The right hand side also 1 upon 8, it is less than 1 upon 8 up to k plus 1 plus 1 bracket close whole square. Solve it, you will get 1 upon 8 2k plus 3 whole square. This is our third equation. Now you see pk plus 1. Here I have written pk plus 1, that is equal to 1 plus 2 plus 3 plus k plus 1. This is the last one. So it is already given that 1 upon 8 into 2k plus 1 whole square plus k plus 1 means, on adding k plus 1 on the both sides Adding, you see I have written here adding k plus 1 both sides in second here. Now pk plus 1, that is 1 plus 2 plus 3 plus k plus 1 can be written like this. You should take the LCM 8 and just multiply it to this side. You will get here 4k square plus 4k plus 1 plus 8k plus 8 whole divided by 8. So 4k square plus 12k plus 9 by 8. So 2k square plus 2 into 2k into 3. This 12k can be written like this. So it indicates that it is a perfect square of 2k plus 3 whole square by 8. As in third, you see in the third I have already stated that it is equal to 1 by 8 2k plus 3 whole square. So 2k plus 3 whole square whole divided by 8 is on the right hand side here. It means that the proposition k plus 1, 1 plus 2 plus 3 plus k plus 1 is less than 2k plus 3 whole square by 8 as in third, you see. So the pk plus 1 is true. Hence, by principle of mathematical induction, Pn is true. Now come to the question number 19. Here the statement is n plus 1 into n plus 5 is a multiple of 3. Say Pn, that is n into n plus 1 into n plus 5 is a multiple of 3. First, the multiples of 3 can be expressed as follows, that is 3, 6, 12, 15, 18 and so on. And it can be again expressed into 3 into 1, 3 into 2, 3 into 3, 3 into 4, 3 into 5. So here the last one, just I have not, it is not the last, but we have taken it. These numbers can be expressed like 3 into p, where p belongs to natural numbers. Now, when n is equal to 1, in the first, we have p1, that is 1 into 1 plus 1 into 1 plus 5, that is 2 into 6, that is 12, and it can be expressed like 3 into 4. So here you see the P1, that is 1 plus 1 and 1 plus 5, 2, that will be equal to 2 into 6, that is 12. Here 3 into 4. It is 2 being the multiples of 3. Because the 12 can be expressed in the form of 3 into 4. Here the 4 belongs to the P. That P is a natural number. So 3P here. The second one. We now come to the assume that the pk is true for n is equal to k. Here you see the pk is k into k plus 1 into k plus 5 is a multiple of 3. Therefore, k into k plus 1 plus k plus 5 is equal to 3p. Third, now we prove that pk plus 1 is true. Now the pk plus 1 can be written here, k plus 1 inside the bracket k plus 1 plus 1, in the second bracket k plus 1 plus 5. So k plus 1 into k plus 2 into k plus 6 is a multiple of 3. So from second, third, k plus 1 we can find it out. You see k plus 1 is here again and k plus 1 here again. So the k plus 1 will be equal to 3p upon k into k plus 5. We have 3p in place of k plus 1. K plus 1 I have written here, the 3p upon k plus 5 and k plus 2 into k plus 6. You see, here the k plus 1, I have written 3p k plus p. First of all, I have equated it to the upper one, that is k plus 1. You see here, k plus 1 is 3p upon k into k plus 5. Now, in place of k plus 1, I have written here that 3p upon k plus 5 into k plus 2 into k plus 6 is equal to 3. Just multiplied it, 3p into k plus 2 into k plus 6 whole divided by k into k plus 5. So the bracket, I have taken it as a q, where q is equal to this, that is p k plus 2 into k plus 6 whole divided by k into k plus 5, and it belongs to natural number. So p k plus 1 is also true, hence by the principle of mathematical induction, Pn is true for all n belongs to natural number.